Okay, so are there any questions about last time or anything else? Right, so we started talking about differential forms on manifolds and integration of forms over singular cubes and over singular chains. So any questions about that? Okay, so if not, then let's start. So 1 second. Okay, so the last thing we saw that was that for any K form omega and any point P in the manifold and any K vectors V1 up to Vk tangent vectors at P, if we choose a singular K cube C such that C0 is equal to P and Vi is equal to DC at 0 applied to EI, then if I look at these family of shrinking cubes, C epsilon of X, which is C of epsilon X, so these are cubes which are shrinking to a point, then the integral of omega over C epsilon divided by epsilon to the K, this converges to the value of omega at P acting on the vectors V1 to Vk. Okay, so in particular, this implies that if the integral of omega over all K cubes is 0, then omega is identically 0. Okay, so that means that we had a map, a linear map phi from the space of K forms omega Kn to the space of K cochains, singular cochains, which was the dual of the space of K chains. Omega goes to the linear functional integral over omega, right? So integral of omega. So integral of omega is a linear functional on the space of K chains, right? This linear map therefore is 1-to-1. Okay, so that means we can view the K forms as a subspace of the K cochains. We can view it as a subspace of the dual of the space of K chains. Now on the space of K chains, we have what's called the boundary operator, which is defined as follows. So given C, which is a singular K cube, we define what are the faces of C, right? So for example, a square has 4 faces. A cube in 3 dimensions has 6 faces. In general, a cube in n dimensions will have 2n faces. So what, or a K cube will have 2 K faces. So what are the 2 K faces? So let I be an index in between 1 and K, and let alpha be from the set 0, 1. So alpha is either 0 or 1. Then we define what's called the C I alphath face, the I alphath face of C. So this will be a K minus 1 cube, a singular K minus 1 cube. So C I alpha applied to x1 up to xk minus 1 is defined to be C of x1 up to xi minus 1. Then in the ith spot, you put an alpha instead of an xi. And then after that, you put xi up to xk minus 1. Okay. So in other words, in the ith spot, you're fixing the value of the ith variable to be either 0 or 1. Okay. So those will give you the boundary faces of the cube. Okay. So as I goes from 1 to k and alpha goes from 0 to 1, you'll get 2k faces. And then you can define the boundary of C, which will be a sum of these faces, Ci alpha, but with appropriate signs. So this is defined to be the sum I goes from 1 to k, alpha goes from 0 to 1, minus 1 to the power I plus alpha, C sub I alpha. So this is a sum of singular k minus 1 cubes. So this is a k minus 1 chain. Okay. So if this seems a bit abstract, let me just draw a picture for you, and you'll see that this gives what you should think of as the usual boundary. So for example, for k equal to 2, what does this boundary operator look like? So this is going from singular k chains to singular k minus 1 chains. So what happens for k equal to 2? Okay. So here's my two-dimensional cube, a square. And so if this is the x1 axis and this is the x2 axis, so this is 0, this is 1 and 0 and 1 here. Okay. So what are the faces? So the faces are, so what is the boundary of C? Boundary C is going to be, so it's a sum, I goes from 1 to 2, alpha goes from 0 to 1, minus 1 to the I plus alpha, Ci alpha. Okay. All right, so let's work this out. When I is equal to 1 and alpha goes from 0 to 1, what do we get? We get minus 1 to the power 1 plus 0 C10 plus minus 1 to the power 1 plus 1 C11 plus minus 1 to the 2 plus 0 C20 plus minus 1 to the 2 plus 1 C21. Okay, so let me write this out. So the first term is minus C10. Okay. The next term is plus C11. And then plus C20. and then minus C to 1. Okay. So let's see what these faces are. What is C10? C10 means I'm fixing the first coordinate. X1 is equal to 0, right? So that will give me this side, okay? So X2 will go from 0 to 1. I'm going to go up this side, but this comes with a minus sign. So I'll get minus of this, okay? Minus of this side. And then I have C11. So that means X1 equal to 1. So that's this side. So this side comes with a plus sign. Okay. And then I have C20. So that means X2 equal to 0. So that's this lower side. This comes with a plus side. So that goes like this. And finally, C21 is X2 equal to 1. So that's the top side. That comes with a minus sign. So this goes like this, but it comes with a minus sign. So if it comes with if this side, for example, comes with a minus sign, integrating over one form over this with a minus sign is the same as integrating over this side with the opposite orientation, right? And similarly, integrating over this top side with a minus sign is the same as integrating with the opposite orientation. Okay. And so what you see is we're getting the boundary of the square, as we should, with the correct orientation, right? So these signs are there so that you get the boundary faces coming with the correct orientation. Does this make sense?
Yes, sir.
Yes.
Yeah, this is okay. All right. Okay. Okay. So this is the boundary operator. So it takes, so this is, first we're defining it for singular K cubes, but the singular K cubes, these form a basis of the space of K chains. So once you define the boundary operator on the basis, then it uniquely extends to a linear map from the whole space of K chains to the space of K minus 1 chains. Okay, so this is the boundary operator. And the main property that this satisfies is that the boundary of the boundary is 0. Okay. So if I apply the boundary operator twice, then I get a linear map from K chains to K minus 2 chains, right? This linear map, this is equal to 0. So I'm not going to prove this, but I've just drawn a picture here to show you, for example, what happens in 3 dimensions. So it's going to be boundary squared is going to go from 3 chains to 1 chains. So you'll get 1 chains. But what happens is that when I look at boundary squared of this cube, then each edge, each one cube is going to occur twice from 2 faces in boundary C. And as you can see in this picture, it's going to occur twice, but with opposite orientations. And so they will cancel out. Okay. Does this make sense?
Yes.
Yes.
Yeah, this is okay. All right. So this picture is basically why the boundary squared is 0. Okay. So yeah, each edge in boundary squared will occur twice in boundary squared with opposite signs coming from 2 different faces in boundary C. Okay. All right. Now, so of course, I should just say that once you know that the boundary squared is 0, then you get a chain complex, right? That means a sequence of linear maps between a sequence of vector spaces. The sequence of vector spaces are the K chains. And this sequence satisfies the composition of two successive maps in the sequence is 0. So that means the image of boundary is contained in the kernel of the next boundary map. And so you can look at the quotient kernel mod image that defines the homology, right, of this chain complex. And that turns out to be the same as the usual singular homology defined using singular simplices. Okay. So, yeah. Okay. So, right. So this boundary square equal to 0 allows you to define the homology of the manifold. All right, but we don't need it really. So I'm just mentioning this. What we will talk about is the following. So the boundary map sends K chains to K minus 1 chains. So I can look at its dual, right? So the dual map is going to go in the opposite direction from the K minus 1 cochains to the K cochains, right? Okay, boundary star. Now sitting inside the K minus 1 cochains, we have the K minus 1 forms. And sitting inside the K cochains, we have the K forms. So then a natural question is, does the dual of the boundary operator, does it send the subspace of K minus 1 forms into the subspace of K forms, right? Okay, I'm identifying these as subspaces of the spaces of K minus 1 cochains and K cochains, right? So the question is, does this dual, does it send this subspace to this subspace, right? Okay. The question makes sense? Yes?
Yes.
Okay. And it turns out the answer is yes. Okay. The dual of the boundary operator, it does take K minus 1 forms to K forms. And in fact, the dual of the boundary operator is given by a first order differential operator D from K minus 1 forms to K forms. So this is the dual of the boundary operator restricted to the space of K minus 1 forms. Restricted to the space of K minus 1 forms, it's given by a first order differential operator D, which is in fact the what's called the exterior derivative. Okay. So let me talk about this for a second. So all right, so we have the dual of the boundary operator, or let me take it from K, K to K plus 1. So sitting inside, we have omega km, and sitting inside here, we have omega k plus 1n. And our question was, whether the image of omega km is contained in omega k plus 1n. Okay. And the answer is yes. the dual of the boundary operator restricted to omega km is equal to a first order differential operator d from omega km to omega k plus 1m. Okay, so assuming this answer, how do we find an expression for d, right? Assuming that this holds, how to find the operator d. Okay, so we're assuming for all omega in omega km, delta star of omega is equal to d omega, right? Now, what this means is for all sigma k plus 1 chains, okay, delta star omega. So this is a linear functional, right? This is an element of ck plus 1 m star. This acting on sigma. So I'm going to write the action as a pairing, all right, between the space of the dual space of k chains with the space of k chains, all right? Okay, this notation you understand? This is the pairing, right? This is an element of ck plus 1 m star, and this is an element of ck plus 1 m. All right, so this dual element acts on this element, right? This makes sense? Yes?
Yes, sir.
Okay, so we're assuming this. So this should be the same as d omega acting on c, right? Okay, this is what we're assuming. Sorry, acting on sigma, not c, acting on sigma. Okay, now what does this mean? Well, let's look at the left-hand side. By definition of the dual operator, delta star, this pairing is the same as the pairing between omega and boundary sigma, right? Yes? This is by definition of the dual operator.
Yes, sir.
Okay, so this becomes the same as the pairing between d omega and sigma. Okay, now omega is a form and d omega is a form, and these are chains. So this pairing is just the usual integration pairing. So this is integral of omega over boundary sigma. This should be the same as integral over sigma of d omega, right? Yes?
Yes, sir.
Okay. Now, I'm sure all of you would have seen this formula before. this is Stokes' theorem, right?
Yes, sir.
So Stokes' theorem is basically nothing but a positive answer to this question that does the dual of the boundary operator send forms to forms? Does it send differential forms to differential forms? Right? And all you're doing is you're identifying what is the dual of the boundary operator. You are identifying it with a concrete differential operator D. Okay. Now, how do we find D from this information? So if this is to hold, right? So then now, so given a point P in N and K plus 1 vectors, V1 to Vk plus 1 in the tangent space at P. Okay. How do we find d omega of V1 to Vk plus 1? So we're assuming this form d omega exists, which satisfies this equation star, right? We're assuming this form d omega exists, which satisfies this equation for all sigma. Okay. So what will d omega p of V1 to Vk plus 1 be? Well, we can use what we did last time. This will be the limit as epsilon tends to 0 of 1 over epsilon to the k plus 1 integral over boundary of C epsilon of d omega, right? Where C is k plus 1 cube such that C0 is P and DC0 of EI is VI. I goes from 1 to k plus 1. Right? This is just what we did last time, right? Yes?
Yes, sir.
Okay, but now we can use this formula star here, right? The integral of d omega over the boundary of, sorry, not over boundary C epsilon, over C epsilon. What am I saying? Over C epsilon, sorry. Integral over C epsilon, sorry. This should be integral over C epsilon. This is the formula that we proved last time, right? Yes? But now, by this property star, this becomes the same as the limit epsilon tends to 0, 1 over epsilon to the k plus 1. So the integral of d omega over C epsilon is the same thing as the integral of omega over the boundary of C epsilon, right? By this property that we're assuming here. Yes?
Yes,
Okay. So that tells us that if such a differential operator, if such an operator D exists on forms, it has to be given by this formula, right? D omega of V1 to Vk plus 1 is going to be the limit epsilon goes to 0, 1 over epsilon to the k plus 1 integral over boundary C epsilon of omega. Okay. So for example, suppose k is equal to 1. Okay. And so omega is equal to, let's say, 8. So let's say omega is a 1 form and say in 2 dimensions to make life simple, n equal to 2, say in R2. Okay. So omega is equal to, say, p dx plus q dy. All right. Now, if I take two vectors, say v and w, how am I going to get d omega? And this is my point P. Yeah. D omega P of VW will be what? Well, what I'll have to do is take a limit. Epsilon tends to 0. 1 over epsilon squared integral over the boundary of C epsilon of omega, right? Yeah. So here that will be basically taking a parallelogram with sides epsilon v and epsilon w. And then I integrate over this, the boundary of this. I integrate over the boundary of this. Okay, right? And I divide by epsilon squared and I let epsilon tend to 0. That will give me d omega of VW, right? Yes?
Yes.
Okay. So let's say, suppose I take d omega of, so I mean, in this case, d omega is a 2 form, right? So a 2 form in 2 dimensions is what? It's just some function h times dx wedge dy, right? Yes?
Yes.
So how do I get h here? H of p. So I mean d omega p of E1, E2 is going to be h of p, right? Because I just apply both sides to the pair E1, E2. Dx wedge dy applied to E1, E2 will give me 1, right? So that means that h of p is d omega p of E1, E2. Okay. So I have to, so this h is just given by d omega p of E1, E2. So to work this out, what I'm doing is now I'm taking a square like this with sides parallel to the x and y axis. Okay. And I'm integrating like this, right? Okay. Now what happens? So basically what's going to happen is when I integrate over the horizontal sides, the dy term will be 0, right? Over the horizontal sides, there's no change in the y coordinate. So this dy term will vanish over the horizontal sides, right? Yes?
Yes, sir.
And
Yes, sir.
you'll only get the dx term. But now what I'll get is an integral p dx over this side, and but minus the integral over this side, right? Yes. So I'll get something like an integral so when I take the boundary, what I'll get? I'll get an integral like 0 to 1. So it's C epsilon, right? So omega of well, okay. So let me so actually what I'll get after a change of variables, it will be, I'll get an integral from 0 to epsilon P of how should I put it? So here my x is changing, the y is going to be fixed. So P of x And then I have y naught. Dx, but then I'll have minus the integral 0 to epsilon p of x comma y naught plus epsilon, right? Dx. That will come from the top side. You understand, right?
Yes.
Yes, sir.
Okay, and I have a 1 over epsilon squared here. Okay. I think this is correct. Yeah, these integrals will be of order epsilon. These are of order epsilon. And now I look at the difference, right? So what will this be? This looks like, so I'll take 1 epsilon out. And then inside I have another epsilon. And this is basically like a partial derivative of p, right? Yes?
Yes, sir.
Okay. So this thing converges to what? This converges to minus this whole thing divided by the epsilon. This converges to minus del p del y, right? Of x comma y naught. Okay. And then I'm integrating from 0 to epsilon and dividing by epsilon. So by the mean value theorem for integrals and continuity, the whole thing will converge to a finite limit minus del p del y of x naught y naught. Okay, where this point p is equal to x naught y naught. Okay, so we're almost out of time. Let me stop and we'll start a new session. Okay. 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 So this calculation is all right. Yeah.
Sir, you have to screen. Yeah, share the screen.
I'm sharing the screen. You can't see it.
Now it is visible. Yes.
Oh, okay. So this calculation is all right. Yes.
Yes, sir.
Yes.
Yeah, fine. And similarly, what will be the other contribution from the other two sides? It's going to be 1 over epsilon squared integral 0 to epsilon q. So along the vertical sides, p dx will be 0, right? Because the change in the x coordinate is 0. So the dx term will vanish. You'll get the dy. You'll just get dy here. So I'll get this side with a plus sign and this with a minus. So I'll get q. So x naught plus epsilon here, right? X naught plus epsilon y dy dy minus the other side 0 to epsilon q x naught y dy, right? And similarly, this will converge. So this is as epsilon tends to 0. And this will converge to del q del x, right? Of x naught y naught. Is this clear?
Yes, sir.
So finally, what do we get? We get that omega, therefore, is h dx dy wedge dy, where h is equal to del q del x minus del p del y, right?
Yes.
Yes, sir.
Okay. So you can see this, so this is d omega, sorry, not omega, d omega. So this is a first order differential operator on omega, right? We're taking first derivatives of the coefficients of omega, basically, right? Yes.
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 And in fact, what would this be? This is equal to actually, so I had p dx plus q dy. This is actually equal to dp wedge dx plus dq wedge dy, right? Because let's do this calculation. I hope the signs are not mistaken. It should come out all right. So what is dp? dp is del p del x dx plus del p del y dy. This whole thing wedge dx plus dq is del q del x dx plus del q del y dy wedge dy. And now what happens? We'll get a del p del x dx wedge dx, but that is equal to 0, right? Because the wedge product is alternating on one forms. Yes? We saw that earlier, right?
Yes.
So dx
Yes.
wedge dx will be 0. Similarly, here dy wedge dy will be 0. So what will remain? You'll get del p del y dy wedge dx, but dy wedge dx is the same as minus dx wedge dy, right? So
Yes.
this minus del p del y dx wedge dy, and from here I'll get a plus del q del x dx wedge dy. So I'll get exactly what we got up here, right? We'll get del q del x minus del p del y dx wedge dy. Is this clear? Okay,
Yes, sir.
because dx wedge dx is 0 and so is dy wedge dy, and dy wedge dx is minus dx wedge dy. Okay. All right. So this formula here, this generalizes to all dimensions. This formula for d omega in the sense that we have the following. So if omega is a K form, say omega is equal to sum over I bar, A I bar, dx I bar, with respect to local coordinates phi equal to x1 to xm near P in M. Okay. And suppose I take V1 to Vk plus 1 tangent vectors at P. So then I have the following proposition, which we will not prove, but you can try to prove it. It's a bit, well, it's not straightforward, but you can try to prove it. But I mean, it's similar to the calculation we did just now for 2 dimensions, that let C be a k plus 1 cube such that C0 is P and DC0 EI is VI. I goes from 1 to k plus 1. Okay. Then the limit epsilon tending to 0, 1 over epsilon to the k plus 1 integral over boundary C epsilon. So C epsilon is a k plus 1 cube. So its boundary is a k cube. So I can integrate omega over the boundary of this small k cube, right? Of the boundary of this small k plus 1 cube, sorry. And this limit exists. And this equals the following form: sum over I bar dAI bar wedge dx I bar. The whole thing, this at the point P, evaluated on V1 to Vk plus 1. Okay. Is this all right?
Yes, sir.
Okay, so we won't prove this, but you can understand where these derivatives of the A's are coming from. Basically, when you integrate over a boundary, right? In the boundary, you have 2k faces, right? Or 2k plus 1 faces rather, and they occur in pairs, right? With opposite signs. So basically, you'll get a difference of 2 integrals here, and these will give you derivatives of the coefficients, like we got here. Do you understand? When I take a difference like this, and I'm dividing by epsilon to the k plus 1, so 1 epsilon will go inside here and give you a derivative. Does it make sense? Yeah?
Yes.
Yes, sir.
Okay, so the derivatives are coming from the pairs of opposite sides. Okay, it's coming from the pairs of opposite sides. Okay, so so we won't prove this, but this means that therefore we can define by virtue of this proposition can define an operator called the exterior derivative d from omega kn to omega k plus 1n such that by defining it locally, if omega is equal to sum over I bar a I bar dx I bar with respect to coordinates x1 to xn, then d omega is sum over I bar dA I bar wedge dx I bar. Okay. And the first thing to notice is that this definition is in fact independent of the choice of local coordinates x1 to xn. Why? So this is well defined. Independent of choice of coordinates phi equal to x1 to xn. Why? Because of this equation here. So let me call this star. By star, why? Because this d omega, as we're defining it using the coordinates, this acting on k plus 1 vectors v1 to vk plus 1, I can write as this left hand side, which is a limit epsilon goes to 0, 1 over epsilon to the k plus 1, integral of omega over boundary c epsilon. The point is this left hand side, this is independent of any choice of coordinates, right? Yes? I'm not using any coordinates to define the left hand side. Is
Yes,
it
sir.
clear?
Right. Right.
Therefore, the exterior derivative is well defined, independent of the choice of coordinates. It equals the left hand side, which is independent of any choice of coordinates. Okay. Okay, so this is because the left hand side of star does not depend on any choice of coordinates. Is this clear?
Yes.
Sir.
Okay. And then it's a theorem which we won't prove, that Stokes' theorem for chains that for all k forms omega, and k plus 1 chain sigma, the integral of omega over boundary sigma is equal to the integral of d omega over sigma. Okay. So this tells us that by what we did earlier, boundary star restricted to omega k n is equal to d from omega km to omega k plus 1. Right? Stokes' theorem is equivalent to this, that boundary star is equal to d. All right?
Yes.
Okay, does this make sense? Yeah. Okay. So any questions at this point? Any questions? Okay. And I mean, just to give you an idea of why Stokes' theorem is true, it's similar to the proof of the fundamental theorem of calculus, that the integral of f prime x dx is equal to fb minus fa, right? That's in fact the one-dimensional version of Stokes' theorem. So fundamental theorem of calculus says what? So basically you think of omega as a zero form on an interval AB. Okay. So zero forms are just functions. So this is a smooth function on AB. Okay, omega is equal to a function f. Okay. And so what is d omega? It's going to be df, right? Which is the same as f prime x dx, right? Yes. So this is in omega 1 AB, right?
Yes.
Okay, and then so I take this is I have to take a one chain. So my one chain sigma is just the identity from AB to AB. Okay, this is my one chain. Oh, it's a one cube. Okay. And what is boundary sigma? This is B minus A. So this is a zero chain. Okay, this is a formal sum of the point B minus the point A. Okay. Right? Okay.
Yes,
And
sir.
so this fundamental theorem, this integral f prime x dx A to B is FB minus FA. This side is equal to the integral over sigma of d omega, and this side is equal to the integral of omega over boundary sigma. Right? Is it clear?
Yes.
Okay. Now, how do you prove the fundamental theorem of calculus? If this is your interval AB, how do you prove the fundamental theorem of calculus? What you do is you divide it up into small pieces, right? You take a fine partition. Okay. And then you start, let's say, from the right-hand side, right? So FB minus FA. Okay. This is equal to a sum over I F T I plus 1 minus FTI, right? So that means the big difference is equal to a sum of small differences, right? Yes, that's all I'm doing. The change in F from A to B is the same as the sum of these small changes, right? And now each of this, by definition of the derivative, since F is C1, this is approximately equal to F prime Ti into delta Ti plus something which is little o of delta Ti, right? Okay. Yes.
Yes, sir.
Okay, and so when I add these up, this becomes like a Riemann sum for the integral of F prime. So I mean, this sum becomes the sum F prime Ti delta Ti plus a little o of 1, right? And so this converges because the Riemann sums converge to the integral. This converges to integral A to B F prime x dx. And this term is little o of 1. This goes to 0, right? Okay. So that's how you prove the fundamental theorem of calculus. Now, Stokes' theorem we can prove in the same way. We just replace this one-dimensional interval by a k-dimensional cube. So here, now we have a k-dimensional cube. So like we chopped up the interval into small intervals. Here we chop up the cube into small cubes. All right. Here we chop up the cube into small cubes. Yeah. And so now, so we get, so chop k plus 1 cube c into let's say n to the power k plus 1 small cubes ci. So ci bar, okay, where I bar belongs to, it's a multi-index. It goes from the set 1 to n to the power k plus 1. All right. Makes sense? Yes? Yeah. Okay. So this is, I mean, basically 1, 2, all the way up to n, and 1, 2, all the way up to n. Right? I'm using these two indices to label the cubes. Does this make sense? Yes?
Yes, sir.
Okay, fine. So then what do I have? Then the key point is this observation that if I look at the boundary of C, this is a sum over I bar. Well, okay, it's not exactly equal. Okay, fine. Okay, maybe I should be a bit careful. It's not exactly equal. What is equal is the integral of omega over the boundary of C. So that's the boundary of this big cube, is the same as the sum over I bar of the integral of omega over the boundaries of the small cubes, Ci bar. Right?
Yes.
Because when I integrate over the small cubes, faces in the inside, which are common to two cubes, these will cancel, right? These will cancel. Okay. So this is like the proof of Morera's theorem in complex analysis. It's the same proof, basically. All right. You're just using the fact that when I sum up the boundaries, the common faces will cancel. So all that will remain is the faces which are in the big boundary. All right. Is that clear?
Yes, sir.
Yes.
Yes.
Now we use this proposition about the exterior derivative, this limit here. What do I know? I know that the integral of omega over the boundary of a small cube divided by epsilon to the k plus 1. This looks basically like d omega applied to the vectors tangent to the small cube, right? So in other words, the integral over a small cube will look like epsilon to the k plus 1 into a value of d omega, right? So what this is going to be is this is going to look like sum over I bar. So the cube has sides of length 1 over n, 1 over capital N. So this will look like 1 over n to the k plus 1 into d omega. So each cube is mapping into the manifold into some point. Let me call it, well, it'll be C of, so if this vertex is say x sub I bar, then it'll be d omega at the point C of x sub I bar applied to E1 to E k plus 1 plus something which is little o of 1 over n to the, little o of 1 over n to the k plus 1. Okay. Yeah. So I get this sum here. This is sum over I bar. Sorry, this won't be E1 to EK plus 1. This will be DC. Okay, wait. So, all right. This will be, I have to take the vectors which are tangent to the face of the cube. So this will be DC at the point x I bar of E1 up to DC at the point x I bar of EK plus 1. And then I have this term which is little o of 1 over n to the k plus 1. Okay. So when I sum up, how many terms are there? Capital N to the k plus 1. And this term is little o of 1 over n to the k plus 1. So the sum will be little o of 1, right? This will give me little o of 1, right? And this term inside, this is nothing but a Riemann sum this term, this first term that I have, this is a Riemann sum for the integral of d omega over c, right? Yes.
Yes, sir.
Yes,
Okay.
sir.
So this converges therefore as n tends to infinity, as the partition becomes finer. This converges to integral of d omega over c, and this little o of 1 goes to 0. Okay, so that's a sketch of a proof of Stokes' theorem. All right.
Yes, sir.
Okay, which is analogous to the proof of the fundamental theorem of calculus. You're just breaking up fundamental theorem of calculus. You break up the big interval into tiny intervals and you add up the changes in f. Here, you break up the big cube into tiny cubes and you add up the integral over the boundary of the big cube. You write as a sum of integrals over boundaries of small cubes. Now, integrals over boundaries of small cubes give you basically values of d omega times a small factor, right? And that this turns into a Riemann sum and the error term goes to 0 and that's it. All right. Is this all right? Yeah. Okay, so this, well, and you can make this rigorous. I'm maybe being a bit, well, sketchy on the proof here, but yeah. This is the idea. This is from actually from Arnold's book, Mathematical Methods of Classical Mechanics, chapter 7 on differential forms. You can look at Arnold's book. It's a very nice book. I mean, and his approach to differential forms is very geometric, you know. So usually in most books, it's very algebraic and you don't understand what's happening. But here, his approach to the exterior derivative is very geometric. The exterior derivative geometrically is nothing but the dual of the boundary operator. Okay. And, you know, the exterior derivative you get by integrating the form over the boundary of a small cube. That's how you get the exterior derivative, right? It's basically by integrating over the boundary of a small cube. An infinitely small cube. That's the idea. Does this make sense?
Yes, sir.
Yes. Yes.
Okay. Yeah, because otherwise, I mean, normally in most books, they just give you the formula for the exterior derivative, this formula here, and you don't know where this formula is coming from and why this formula and so on. I mean, when I first saw this, I didn't understand why do you take this formula, you know, where do you get this formula from? So hopefully this calculation that we did in 2 dimensions will help you to understand where this formula is coming from, right? You pick up derivatives of the coefficients when you integrate over the boundary of a cube. All right. Okay. So any questions? Any questions? Okay, so I mean, the proof of Stokes' theorem you can do in a way which is analogous to the proof of the fundamental theorem of calculus. And in fact, I mean, the definition of the exterior derivative that we gave in terms of the integral over the boundary divided by epsilon to the k plus 1 limit, this is similar to the definition of the derivative of a function, right? In one variable calculus, what is it? It's limit fx plus h minus fx divided by h, right? Limit h tends to 0.
Yes. Yes.
Yes.
The same as the integral of f over the boundary of the interval x to x plus h divided by h. Yes?
Right.
Yes, sir.
So this definition generalizes the definition of the usual derivative f prime x from calculus, right? So in that sense, the exterior derivative really is a derivative, right? It justifies the name exterior derivative for this operator. Okay, yeah. So any questions or comments? Okay, so we have less than a minute. So let me end this session and we'll start a new one. Okay. Okay. All right. So now, so we have the exterior derivative. And so here are some properties I won't prove. Well, one property is easy to prove, that d squared is 0. D of df is 0. How do you prove this? This is easy. You don't need to do any calculation, nothing. It's just a one-line proof. Any idea? How do you prove
Del
this?
square is 0. So
Right, exactly. So del star squared is 0, right?
yes.
And del star is equal to d, restricted to forms. Del star is d. So therefore d squared is 0. That's it. Exactly. So it's just because d is the dual of del that d squared also is 0. You don't need to do any calculation, nothing, you know. So, I mean, avoid calculations whenever you can, right? That's the motto, is to avoid calculations whenever possible. Okay. All right. So we have Stokes' theorem. Okay, now I'm going to come to something which is going to be important for us. So this you may have seen in you would have seen in your algebraic topology class. When you have a homotopy, you get something called the prism operator, right? Yes, have you seen this in your
Yes,
algebraic
sir.
topology? Right. So we're going to do the same thing with cubes. In algebraic topology, you do it with simplices. So it's a bit more complicated. With cubes, it's much simpler actually. You have, yeah, so it's much simpler with cubes. So we have the following. Suppose M and N are smooth manifolds, and I have a homotopy H. So that means a map from M cross the interval 0, 1 into N. And suppose this is a smooth homotopy. Okay. So this H, capital H, gives us a one parameter family, a smooth family of maps from M to N, right? HT, where HT is a map from M to N, such that HT of X is capital H of X comma T, right? So let's call H0 to be F and H1 to be G. All right, so capital H is a homotopy between the maps F and G. Okay. Now, this homotopy leads to what's called an associated prism operator, which is a linear operator from k chains in M to k plus 1 chains in N, which is defined as follows. So again, to define an operator on the space of k chains, I just need to define its value for a k cube, because those are a basis, right? And then it extends uniquely by linearity to the whole space. So let's take a k cube in M, C. Okay, it's a singular k cube in M. So you define P of C. This is going to be a k plus 1 cube in N, a singular k plus 1 cube in N. So it's defined by the following formula. So it's going to be a function of k plus 1 variables, taking values in N. The first variable I think of as time, t, and the other variables are space variables, x1 to xk. So PC applied to t of t comma x1 to xk this is simply defined to be ht of c of x1 to xk. All right. So geometrically, what are we doing? We have this map C, which is a k cube. So which is defined on, let's say, on the bottom of this cube here, right? It's defined on the on 0, 1 to the k. All right. So C is defined on the bottom here. This maps into m, sorry, and then I have the homotopy. So now the homotopy is a one parameter family of maps, right? So this is going to map under the first, under H0, it maps to some bottom here. And then as t goes from 0 to 1, it maps to a one parameter family of k cubes in n, right? So over here in the middle, for example, is the image of ht composed with c, right? And at the top, I'll have g composed with c. At the bottom, I'll have f composed with c. Does this make sense? So this is my k plus 1 cube in n. Okay. Yeah, so basically what I do is I map my the bottom of the k plus 1 cube by c into m, and then I map it across by each of the maps ht. That defines a map from the k plus 1 cube into m. Is this clear, this picture?
Yes, sir.
Okay. So this is the prism operator. Okay. Now let's work out what will be the integral of a k plus 1 form in n over this k plus 1 cube. Okay. PC. So PC is going to be a k plus 1 cube in n. So to work that out, we need to pull back by PC. So to pull back, we need to compute the derivative of PC, right? So PC of t comma x1 to xk, this is ht of c of x1 to xk. So this is the same as h of c of x comma t, right? Now, what is the derivative dpc at a point tx applied to E1? So the E1 direction is corresponds to the t variable. So this is del t, right, of PC of t of x1 to xk. So this will become del h del t applied to cx comma t, right?
Yes.
Okay. And now, what about the other basis vectors? As I goes from 1 to k, dpc applied to ei plus 1. So the I plus 1th variable corresponds to xi, right? So this will be del xi of ht of c of x, right? And del xi of this, by the chain rule, this will be dht at the point c of x applied to dcx of ei. All right?
Yes.
Okay. Okay. So therefore, if omega is a k plus 1 form in n and c is a k cube in m, then the integral of, we can integrate omega over p of c, because p of c will be a k plus 1 cube in n, right? So now this integral, by definition, it's an integral over 0, 1 to the k plus 1. So by Fubini's, I write it as, so it's an integral with respect to k plus 1 variables, t and x1 to xk. So I write the integral dt inside and the integral x1 to xk outside, all right? So outside I have integral over 0, 1 to the k. Inside I have integral over 0, 1. And then I'll have omega of pc of tx. So that is ht of cx. And then inside I'll have the derivatives of PC. So the first one will be del h del t of cx comma t. Then I'll have dht at the point cx of dcx of E1 up to dht of cx, dcx of ek, dt, right? Now, this thing inside this integral 0 to 1, this is, I can write the whole thing as the integral over 0, 1 to the k of the pullback C star of a form P star omega. Where what is this form P star omega? Now P star omega, this is a K form on M. Okay, P star omega is a K form on M. What is the value of P star omega at a point P acting on K vectors V1 to Vk? It's defined to be the integral of from 0 to 1, omega at the point ht of P of del h del t of P comma T, dht of V1 up to dht of Vk dt. Right? Now notice that this right-hand side, this is alternating and multilinear in the vectors V1 to Vk, right? Because omega is multilinear and these dht, these derivatives are linear, right? So this is multilinear in V1 to Vk, right? So this is a K form on M, yes?
Yes, sir. Yes.
Okay. So what is this K form? This K form is nothing but the following. So what you're doing is I have my point P here, and I'm taking vectors V1 to Vk. Okay. And now what I'm doing is I'm mapping across by all of the maps ht, and in fact the derivative of ht. Okay. So what's going to happen to P when I map under ht? P is going to move along a curve, right? So this is in M and this is in the manifold N. Okay. So this point is f of P. This point is g of P, right? Inside, in the middle, I have ht of P, right? And the derivative is going to map these two vectors, these k vectors, to k vectors here. So this is dht v1. This is dht vk. Okay. Now what do I have? Omega is a k plus 1 form on N. So omega has to act on k plus 1 vectors. So here I have k vectors, dht v1 up to dht vk. I need one more vector, right? What is that extra vector going to be? What is the last vector going to be? Any idea? It's going to be
Of ht.
Exactly. So it's going to be the tangent vector to this curve, right? It's going to be tangent vector to this curve. So this will be del h del t of p comma t. Okay, so that gives me these k vectors, and then I let omega at the point ht of p act on these k vectors, del h del t of p comma t, dht v1, dht vk, and then I integrate this from 0 to 1 dt And this is defined to be P star omega at the point P, acting on the K vectors V1, 2. Right?
Right.
Okay, so P star omega is a K form on M. Okay. Right. So what we're doing is the following. We have, I mean, basically this is it, the picture. So this is my K+1 cube. So I have at the bottom, I've got C here. This is mapping into M. And then I map across by all the HTs. So I get this picture here. I get the, sorry. Yeah. Okay. Now, what will the integral of omega over this? So this thing here is this thing is PC. So this is a image of PC. Now, what is the integral of omega over this big K+1 thing? It is basically what you can do is you do a Fubini's. You divide up C into small pieces, the bottom here, right? And then so at the bottom you get these vectors E1 to EK. And then we do what we did in this picture here, right? I get vectors V1 to VK here. And so that will give me vectors here. And then I flow them along. Right? So I'll get vectors along here. And I'll get the tangent vector here. Right? Okay. You see? And so the integral of omega over PC turns out to be the same as the integral over C of P star omega. Does this make sense?
Yes.
Yes.
Yes, sir.
You see the picture, right? Here, basically, I'll be dividing into small things. So basically, this bottom will get divided. Right? And for each point in the bottom, I'll get an integral from 0 to 1. So basically, I'll get an integral over C. And then for each point corresponding to C, I'll get an integral 0 to 1. That will be my P star omega. All right. So what does this mean? Abstractly, what are we doing? We had the map P, which was going from CKM to CK+1 N. So the dual P star is going to go from where? It's going to go from CK+1 N star to CKM star. Now sitting inside this CK+1 N star, I have omega K+1 N. And sitting inside this, I have omega Km, right? And what this formula says is that the dual of P sends the space of k plus 1 forms in N to the space of k forms in M. And the dual is given by this explicit formula that we had, all right? That we have here. Is this clear?
Yes.
Okay, so in this case, it's easy to see that the dual operator of the prism operator, it sends forms to forms. Okay, so it sends k plus 1 forms on N to k forms on M. Okay, this formula expresses the duality, right? This formula expresses the duality. Just like we did for the exterior derivative, I mean, for the boundary operator. Similarly, we're doing it for the prism operator, right? Is this clear? Yeah.
Yes.
Okay. Okay, fine. So we have this. So now, now what happens is I want to look at now an infinitesimal homotopy. Okay. So infinitesimal homotopy now means the following. Okay, so I have my k plus 1 cube here. So this bottom is this 0, 1 to the k, that the whole thing is 0, 1 to the k plus 1. And what I want to do is just restrict to the time variable. You think of the time variable as the vertical direction, and these directions are the space variables, x1 up to xk. The time, I'm going to take the time to be infinitely small. So I'm just going to look at a small slice of this, all right? Okay, a very thin vertical slice. Okay, this is epsilon, which tends to 0. Okay, so then I can look at the image under this. So that will be a very thin, k plus 1 cube like this. Right? And what will happen to the integral? So let me call this thing now P epsilon. Okay, so P epsilon C of Tx, this is defined to be PC of epsilon Tx. All right? Yes, where epsilon is very small and positive. Okay, I can do this. Yeah. So this is what I mean when I say infinitesimal homotopies. I'll be looking at a homotopy where in the time direction I just move a small amount. All right, I just flow for a small time. So what happens when I flow for a small time if I integrate? Well, basically the vertical direction, it basically infinitesimally, it looks like a vector field, right? It looks like a vector field along the k cube, right?
Yes.
right? Infinitesimally, it looks like a vector field. So what's going to happen to the integral of omega along P epsilon C? Well, this should tend to 0 as epsilon tends to 0, right? Because in this direction, the length is going to 0, but it should tend to 0 like constant times epsilon, right? So I should look at this divided by epsilon, right? And this, I should hope, converges to some limit as epsilon tends to 0, right? So before doing the calculation, let's just try to guess what it should be. Well, when I integrate, what am I going to do? Basically, I'm going to look at omega acting on over here. Like if I take a small section here, I'm going to look at omega acting on vectors tangent to the base. So some v1 to vk. And then I'll have one direction pointing up, right? Which is, say, a vector field x, which is the del del t at t equal to 0, the time derivative of the homotopy, right? Yes?
Yes, sir.
So what should I get? Basically, I should get the integral over C of a form called the interior contraction Ix omega, where Ix omega of V1 to Vk is defined to be omega of x comma V1 to Vk. Okay, so at a point P, basically it will be x at P comma V1 to Vk. Make sense?
Yes, sir.
Okay. All right, so let's prove this. So now let's come back to the notes. So I'm just going to do this for a homotopy from the manifold to itself, not from the manifold to another manifold, but from the manifold to itself. So suppose I start with a vector field x on M, and I let phi t be the flow of x. So that gives me a homotopy. So there's a typo here. The homotopy goes from M cross 01 to M, not to 01. This should be M here. Okay, what is the homotopy? It's x comma t goes to phi t of x, right? The homotopy, the flow gives me a homotopy, right? My maps ht are just the flow maps phi t. Okay, so then I have an associated prism operator p. Now for epsilon between 0 and 1, I define p epsilon c of t comma x to be pc of epsilon t comma x. So what is this? This is going to be phi sub epsilon t of cx, right? Okay, this is my small prism, yeah, where in the time direction, I just move by an amount epsilon, okay? So now this, I can look at the corresponding operator on forms. So let me call that p epsilon star omega, right? Yes, this will give me an operator on forms, this prism operator. It will take k plus 1 forms to k forms on M, right? P epsilon star. So what will p epsilon star be? It will be an integral from 0 to 1 omega at the point in the homotopy, that's phi epsilon t of p. And then I have in the first slot the time derivative. So del del t of phi epsilon t of p. And then d phi at d phi of d of phi epsilon t applied to V1 up to d phi epsilon t applied to Vk, right? Yes, this is my corresponding operator P star, right? P epsilon star, right? I'm
Right.
just using this formula here. Okay. Fine. So now I divide the whole thing by epsilon. Okay. So I take 1 over epsilon P epsilon star omega. So this is 1 over epsilon into this omega of this. Now, what is del del t of phi epsilon t? Well, del del t of phi t is x, right? Yes, it's just the derivative of the flow gives you back the vector field, right? So by the chain rule, when I have an epsilon t here, I'll get an epsilon times x here, right? It's just the chain rule. Yes?
Yes, yes.
Yes, sir.
So del del t of phi epsilon t of p is going to be epsilon times x at the point phi epsilon t of p. Okay. And then the rest stays as it is. So this epsilon will come out because omega is multilinear. This epsilon will come out and cancel with this epsilon. So I'll just get an integral 0 to 1, omega at the point phi epsilon t of p, x at the point phi epsilon t of p, d phi epsilon t of v1 up to d phi epsilon t of vk, integral dt, right? Now as epsilon tends to 0, this whole thing is a continuous function of epsilon. So as epsilon tends to 0, I can just put epsilon equal to 0. And then what will I get? This phi epsilon t will become phi 0, which is identity, right? So this will become omega at p applied to x at p d, well, d phi epsilon t. This is derivative of the identity, it's just the identity. So this will just become v1 to vk. So the whole thing tends to omega p applied to xp comma v1 to vk. Is this clear? Yes?
Yes, sir.
Yes, sir.
Okay. So therefore, 1 over epsilon, p epsilon star of omega, this converges to what's called I sub x of omega, which is now a k form, where for omega, a k plus 1 form, Ix omega is called the interior contraction of x with the of omega with the vector field x. It's defined as follows: Ix omega at p applied to v1 to vk is omega at p applied to, you just put an x in the first slot, x at p, and then you put v1 to vk in the remaining k slots. Okay. So from a k plus 1 form, I get a k form. Okay. So this is the interior contraction. So the interior contraction I can think of as coming from an infinitesimal homotopy in the direction of x, right? That's how this interior contraction is coming, right? I mean, what does it mean? It means if I look at the integral of omega over a small prism, p epsilon of c, and I divide by epsilon, then this is the same as the integral over c of 1 over epsilon p epsilon star of omega, right? And now this form inside is converging to Ix omega. Therefore, this integral converges to the integral over c of Ix omega. Okay. So that is the picture which I drew here, right? That's what we wrote here. The integral of omega over p epsilon c divided by epsilon. This converges to the integral of the interior contraction over c. Is this clear?
Yes, sir.
Okay. So we've proved this. Now we can come to a very important formula for us, which is called the Cartan formula. So we'll finish with this today. So, okay. So suppose omega is a k form and x is a vector field on n and phi t is the flow of x. Then like we define the Lie derivative of a vector field with respect to another vector field, we can similarly define the Lie derivative of the form omega with respect to x. So this is again going to be a k form. so Lx omega, this is just defined to be d dt at t equal to 0 of phi t star omega. Okay, so omega is a k form, so phi t star omega is a k form. And so pointwise, as t varies, I get a one parameter, a curve of k forms at each tangent space. I just differentiate them pointwise, okay, at t equal to 0. All right. So this defines the Lie derivative. And the point is that the Lie derivative is 0 if and only if the k form omega is invariant under the flow. That means phi t star omega is equal to omega for all t, if and only if Lx omega is 0. So, okay, so that you can just check this calculation. It's an easy calculation. I'll omit it for lack of time. So now, what do we want to do? We take the prism operators P epsilon associated to the homotopy phi t, where phi t is the flow of x. Now I take C, a singular k cube. Then what we want to do is compute the boundary of the prism operator. So look at the boundary of P epsilon C. So what should this be? Well, you look at this prism. So the boundary, visually, it's easy to see what the boundary is, right? It should be the top minus the bottom and then minus the vertical sides. Now, what are the vertical sides? The vertical sides are nothing but the prism operator applied to the boundary of C, right? If the boundary of C are these edges, this square. So each edge here, when I apply the prism operator, will give me a vertical square like this, right?
Yes.
So
Yes,
the
sir.
boundary, the vertical sides will be just the prism operator applied to the boundary of C. Okay. So you can compute, this is an easy computation. The boundary of P epsilon C is the top minus the bottom minus the vertical sides. The top is phi epsilon composed with C. The bottom is C and then minus P epsilon of del C. Now we integrate. So we look at 1 over epsilon, integral of omega over the boundary of P epsilon C. Okay. Note that C is a k cube, so P epsilon C is a k plus 1 cube. So boundary is again a k cube. Okay. So we can integrate omega over this. So this becomes 1 over epsilon, integral omega over phi epsilon composed C minus integral over C minus 1 over epsilon integral over P epsilon boundary C. And this becomes, this right hand side becomes integral over C phi epsilon star omega minus omega. And I have a 1 over epsilon here. And this integral over P epsilon over boundary C is the same as integral of P epsilon star omega. And I have a 1 over epsilon. And here, this P epsilon I can put as a P epsilon star d omega here. Oh, sorry, this integral over the boundary becomes a d omega by Stokes' theorem over P epsilon C. And now I just take limits as epsilon goes to 0. So this P epsilon star d omega into 1 over epsilon, that will converge to Ix d omega, integral over C. This phi epsilon star omega minus omega over epsilon, this converges to Lx omega as epsilon goes to 0. And as we've seen, this boundary C here, I can put this inside as a d, integral over C of d of this. And so this converges to d of Ix omega. Okay. Okay, we're almost out of time, so I'm going a bit fast. But it just follows from whatever we've done so far. Is this clear? Yes?
Yes, sir.
Yes, sir.
Okay.
Yes.
So now this is true for all C, and therefore, if two forms have the same integrals over all cubes, then we know that they're equal, right? Therefore, we get that Ix d omega is equal to Lx omega minus dIx omega. And so this gives us what is called Cartan's magic formula for the Lie derivative. Lx omega is equal to dIx omega plus Ix d omega. Okay. All right, so we're out of time. So let me stop here. And we'll continue on Thursday. Okay.
Okay, sir.
Okay. Thank you.